remember, flow is going to be equal to a change in pressure difference over resistance. So what affects resistance, and specifically vascular resistance? Remember, we can actually use the same equation. I think it's actually not remember. This is the first time I'm telling you this. You can switch around this equation to solve for resistance, and that's going to help us figure out how you alter resistance. If we multiply both of these sides by resistance and solve for resistance, we then divide by flow, we're going to get this. Same thing, resistance equals a change in pressure over flow. So that's solving for resistance. A similar equation to this, I'm going to show you. You do not need to memorize this, but it can help to make sense of the factors that affect resistance. This is another equation for resistance. R is resistance, right? R. So this is going to be a way that we can look at the factors that affect resistance. They're right here. Radius, length of the vessel, and blood viscosity. So those are the three things. I'm going to go through them. We'll go through the top ones first, the numerator. So these are going to be things that increase blood resistance because they're on the numerator. So as these get bigger, resistance gets bigger. So the first one is viscosity. What's viscosity? The thickness of something. So stickiness. So a viscous fluid is honey. Water is not as viscous as honey. Oil is more viscous. So it's the thickness or stickiness of a fluid. And blood is variable in viscousness. It's more viscous than water, right? The plasma portion of blood is going to be less viscous, but blood overall, whole blood, has some, substance to it. And that can potentially change over time, but it's fairly constant. There's conditions such as, we looked at excessive numbers of blood cells that was mentioned, polycythemia, and that can increase resistance if you have too many red blood cells. But under normal circumstances, this isn't a variable that's going to change a whole lot in one individual. In cases of anemia, that could potentially change. So this is, again, increased viscosity equals increased resistance. This is true basically just on common sense, right? Honey doesn't travel very well through a tube. It's basically the molecules can't slide past each other very well. That's literally what resistance is. So that is a factor. I want you to know it's not going to be relevant for regulating blood pressure, but it is clinically relevant in terms of if you had altered viscosity. The other numerator is length. So as you increase length of what, like the vessel, the tube, you're going to increase resistance. So that's just kind of like the longer it takes to get through the tube, the more resistance is encountered. So longer tube equals more resistance. So this is also something that doesn't change in your body. Besides from like infant to adult, you actually do have changes. So kids actually have lower resistance in their circuits, their circulation, and lower blood pressure. That's one reason for blood pressure rising as you become an adult and grow. Your blood vessels get longer and have more resistance. And then you have the higher blood pressure to push through them. Okay, last one is a denominator value. So both things so far were things that if you increase them, it increases resistance. This is one that is inversely related to resistance. So that means as you increase it, resistance decreases. This is R equals radius. And then of the lumen, we're just going to say the inside of the vessel, that's the lumen. We talked about diameter of the blood vessels before. how is radius related to diameter? It's 2 times diameter. So you could use 1/2 diameter. It's just that's what's radius is this calculation. Notice it's 4 to the radius squared times pi. You do not need to know that. So radius of lumen, as this increases, you're going to decrease resistance. And that makes sense, right? This should be somewhat intuitive. As you have a constricted tube, you have less flow. This is due to friction. A larger tube is going to have increased flow. There's less friction. So it also depends a little bit on the volume in there, but just given bigger or smaller, right? Think of like a tube of water. If you have, or a channel like a river, as you get smaller and smaller streams and rivers, you have more resistance in those streams. A big single channel of water can have very quick flow due to having less resistance. And in that case of the river, the resistance is like the sides of the river, the rocks, the bottom of the river. In our blood vessel is actually the sides of the vessel. So there is friction all along the sides of the vessel where the fluid is passing through. One more thing about that. Okay, because of this is back to surface area. So in this large vessel, the blood lower proportion of the blood is touching the side of the vessel. So you can have blood fill up this entire tube, and this blood in the middle here has no resistance. It's not being slowed down by friction. There's a larger amount of blood that's hitting the side of the tube here. So it's more of it is going to be slowed down. This is really important. First of all, changing resistance is going to dramatically change resistance. Changing radius is going to dramatically change resistance because of this quarter power here. So changing resistance a little bit changing radius a little bit changes resistance a lot. Changing viscosity does not change resistance as much because we're just multiplying by 8. Cubing, going something to the 4th is always going to be more, so r to the 4th, than multiplying something by 8 times. So like length. We'll see an example of this in a moment. This is also important because this is the thing that our bodies can regulate and change. That is going to be vasoconstriction and vasodilation. So this can be rapidly changed in the body to allow for regulation of blood pressure. And that's what we'll see. This is the way our bodies regulate blood pressure, the main way.